So what do we have today? Well, it seems that we have a glorious mystery box of mystery, which we shall open and figure out what this mystery is. Oh no, not this guy again. Last time we saw this guy, he didn't integrate very well. So let's see what we can do with that. And let's open up our hint box, which is rather lovely. So this here is our basic Maclaurin series, and it's going to help us a lot in this case. So, as most people with experience in series and expansions know, that e to the x can be written like this, as the infinite sum of k starting at 0 going to infinity of x to the k over k factorial. Now, we can easily substitute x for negative x squared, and we can yield a new series, which I'll do over here. And we can write it like this. It's still going to start at k equals 0 and run to infinity, as it's a basic substitution. But instead, it is going to be negative x squared to the k over k factorial. So let's simplify this series and bring it down into a better form for us to deal with. So this is negative x squared to the k. We can easily just use our algebra of powers, and we can manipulate this around a bit to get negative 1 to the k x to the 2k over k factorial. And we can't forget our sum. The sum is very important. So, as can be seen, this is just a simple polynomial series, and polynomials can be integrated very easily. So what we're going to do is we're just going to integrate this x to the 2k term, and we can easily pull a majority of the inside out because they're all constants. So we're going to take out the k factorial and the negative 1 to the k and throw them to the outside. And now we just have to deal with x to the 2k inside dx. And this is very simple. We can just use our basic rules of integration here for powers and get an answer. Very straightforward answer. And this shall become negative 1 to the k times x to the 2k plus 1 over k factorial 2k plus 1. Now, well, I bet you're thinking to yourself, that was simple. We just integrated this function, which has, as I had said earlier, was non-integrable. Now, although that seems fairly straightforward, this is actually a special function that we've just yielded here. And it is not a closed function. So basically what that means is you can't just put it in and get a straight out answer. you can really only get approximations, and for some values it does converge. It does converge for all values, but it's hard to figure out exactly what it converges to in terms of known constants or known functions or closed functions. So this here is a special function, and it is in terms of what is called the error function. We're going to look at the error function. So the error function is defined by Earth x is equal to 0 to x e to the negative t squared dt. And then we're going to multiply it by 2 over root pi. Now, why would we multiply it by 2 over root pi? This has to do with something in statistics, because this is where it comes up the most. So, this function here is a result of us integrating 0 to x e to the negative t squared dt. Now, in my last video, we proved that the area under this entire curve is equal to the square root of pi. So the area from 0 to x, if x were to be infinity, must be equal to root pi over 2. And that is where this comes from, this being multiplied by the 2 over root pi. Our error function needs to be normalized out so that it's asymptotic to 1, not some other funny value that you wouldn't want to deal with in statistics. So how would we define this? We can actually define this very easily, and this is going to be equal to root pi over 2 Earth x. Now, this is useful in statistics for finding out how much you have under the bell curve, and this is useful for figuring out areas under portions in the bell curve, as it can be easily rewritten like this using our fundamental theorems of calculus. And this is where approximations for the area under the bell curve come from. So you could just set your A and B and find out how much of the whole occurs in there. And this is very useful. It's used in statistics for working with the bell curve and for finding out how much is within certain areas of it. But the problem is that you still can't get that full answer in terms of elementary functions, and that's going to be remaining a mystery for a while, even to the best mathematicians. So this is the end of our first video for special functions. And hopefully in the future we'll be able to do some Hankel functions and some Bezel functions and possibly even some functions of complex numbers, which I'm really looking forward to. So thanks for watching, and until next time, do some math.